So now let's start the I would say like a end chapter of that whole thing is the continuum system. So let's start like how we can able to derive the equation of motion or differential equations for a continuum structure. Okay, so in continuous structure, so suppose if we try to recap what we have studied before, so we have seen that first we did with the single degree freedom system, then from there we went for the multi degree freedom system. In single degree freedom system, we primarily have a spring mass, means spring and a mass. So we are idealizing the full system into a single spring and a single mass system. Okay, then we went to the much better model, that is a multi-degree freedom model, where instead of a single mode we are taking, means a single spring mass system, we are taking a multiple spring mass system. Okay, we have also seen that how we can able to calculate the dynamic responses for both the system, single degree and multiple degree. We have so responses contains the 3-4 different things. For example, first it is the eigenfrequency estimation, means what are these natural frequencies, then how the structure will respond in terms of the free vibrations, then how will it respond in terms of force vibration, also force vibration in the time domain and frequency domain. So that we all checked throughout this thing. Okay, but then another important thing actually get remained, that is how the structure, means all the things are like approximations. Now suppose if we try to solve a beam or a bar or a plate or cell, whatever, as like as it is, then how can we able to solve it? Because suppose for example, if we let's think like we have a bar. So bar means we know this is like a rod type structure. You can think it as like a member of the truss, so where only axial components are active. Okay, so in that case, what are the forces acting on that? Forces will be act on the along the direction, axial direction, the forces can act. Okay, so if we think that if we try to idealize that full system as a single degree freedom system, what we will try, like suppose you, let's say like you hold that bar one end and you are pulling it from the other end, or you are giving some dynamic excitation at the other end, how the structure is going to respond. So you can think like, okay, I will think the spring and the mass. So mostly your thought process is something like that. Okay, try to accumulate the full mass, put it there, and also the stiffness is something like EA by L. So that will be mostly the stiffness. That is A into rho into L will be the mass. So mostly suppose if you think that this one has the Young modulus E, area E, and length L, maybe people will think that okay, I will put it A by L, as this is the stiffness of the full bar, and maybe you will think that mass will be rho A times L, maybe some factor need to be multiplied, and they will more or less able to get a single degree freedom system from that. But if you see, but that does not consider many of the things. First thing is where, if you see, now suppose if you make that approximation, then maybe you will get some level of dynamic responses will be matched. Like for example, you applied a particular amount of force, how much displacement you are about to get, that may be matched. Okay, but if you try to see how the total vibration happening inside the body, you cannot able to get that, because that information is lost, because you have approximated the model, so that information is no longer there. So maybe you may think that okay, let's not make it in a single degree freedom. Why not if I try to make it like this way? Some number, like you can think that okay, this is like a full bar, you start discretizing it into like 4 parts. So each part you are putting like this. Could be one of the thought. Something similar to the finite element, as we are doing it, like we discretizing it and then try to make that mass matrix and try to solve it. That also one way possible. But still, and there you can say that your approximation or your results will be much more closer, and you will try to get much better output. For example, if you try to calculate the mode shapes, like here you should get like throughout the displacement domain, throughout the domain, how the displacement is varying, that you should able to get. But here it will be like a discrete points you will get, and then you have to just join them. You will have no other choice to do. Okay, so these are some of the, and also additionally one important point is there. If you see, like if both the models are, like suppose if I say this is my original MO model original, this is model 1, this is model 2. If you say that model 1 and model 2 both could be the representation of model 1, then there is some question also comes into picture. First point is that model 1 has a single degree freedom. So if I think how many natural frequencies can be possible? Only one. So that will correspond to a single mode also. Very simple. Now if I think model 2, let's say it's a 4 degree freedom system. So how many natural frequencies can be possible? 4. And it will be correspond to the 4 modes. Okay. Now what is the, how many natural frequencies you can expect from MO, means the original model? Infinite, exactly, because it's a continuous system. So you can see that these all are always the approximation. You are not getting exact things. You are maybe approximating mode. Yes, now maybe there is could be some point that okay, will the higher mode have that much of significant contributions? Agreed. They may be not having that much of significant contributions, but yeah, some sort of precise analysis you may need those things. Okay, so for that reason, actually, if you see that to fill that gap, people have also studied the continuous system, and continuous system as it is, not like any approximated version. Okay, so now suppose if you try to do the continuous system as it is, how will you go do that? So let's first take the bar problem. Okay, so once we are making this type of like a reduced system or like a single degree multi-degree freedom system, so what is the first thing we do? We try to write the equation of motion. Okay, so here also the same thing we have to do. We have to first try to make the equation of motion. How we can able to make the equation of motion for that? So you can think that we can just cut a portion, maybe let's say at x distance we cut a portion, so that part is like this, which has a length dx. Now if you think this is having the Young modulus E, area is A, okay, and density is rho. So how much mass does that element have? So mass of that, so suppose if you just think like this one, then area is this area, and so how much mass this thing has? Rho into A into dx, that is the amount of mass. Okay, now you can think that this small element is moved by ux amount. Why I am putting x? Because that is at the x distance that much displacement is happening, so I put it ux. Okay, so how much will be the inertia force will come? Inertia force will be rho A ux double dot dx. Am I right? And now if you think that how much, and now you think like here there is a force acting on it, that is F, and this side you have a force F plus del F del X. Okay, and that del F del X force will be how much? So you will have, so now if you think that how your balance is happening, and that del F del X force is also how it will act. So del F del X EA Young modulus into area times how will that be? Okay, so first let's assume that way. So now if I try to just write the equation of motion, so if I see F plus rho A minus F minus del F del X is equal to 0. F gets cancelled out. Okay. So rho A into d2u dt2 into dx minus okay. So how we can able to get that? How much is the difference in the forces? Difference in the force we can able to get from first strain and how much displacement happened. From there we can able to get how much is the strain. From strain we can able to calculate how much is the stresses and all those things. Okay. So now if you think that end part which is the dx amount that get extended by ux amount. So strain is equal to del u del x is your strain. Okay. If strain is del u del x, what is the stress? E into del u del x. Okay. Makes sense? Now, if this is the so what is the force? How much? EA into del u del x. Okay. Now, what is the del F over del x? That will be EA into del 2u del x2. Make sense? Any doubt? Good. So we will get that, and that full thing is happening with the dx one. So then the dx will be multiplied with that also. So rho a into del 2u del x2 into dx, that is equal to 0. Now if I cut the dx out, so I will get the equation del 2u del t2 minus ea del 2u del x2, that will be equal to 0. Make sense? Do you get that? So if you think u is like a displacement vector, so that is dependent on the two parameter x and t. So with position and with time that are varying. Any doubt up to that? All okay? Very good. So we got that point. Now what is my objective? What is known first of all? So that is the equation of motion. All of you agreed with me. Is it the equation of motion? Agreed? Yeah. Now there is 2-3 things you have to first understand. That is the equation of motion for the domain. Means suppose we are like, once we are talking a continuum system, like let's say this is a continuum system, we try to model it as like that. So in that case, in that pin, complete domain equation is this. Inside that domain, this thing is valid, but there is also 2 other conditions, that is at the boundary. What is happening? Okay, so this thing is happened in the domain only, and then we have some sort of boundary conditions, and we have also initial condition. So if you try to correlate with the previous study, when we were discussing on the discrete systems, whether it is multi-degree freedom, whether it is single degree freedom, we do not have the parameter x. We have no effect on the parameter x on the equation of motion. But now we have the effect of parameter x on the equation of motion. Did you notice that point? That is one of the very, very important point to note, that in the discrete system, we do not have any consideration of the space. That full equation of motion is just only looked based on the time variation. But here we are having the consideration of the space as well. That means where the system is, what is the length of the system, all those things are actually becoming crucial. But we do not have those effects in case of the single degree freedom or multi-degree freedom system, means a discrete system. That position is not a required parameter. Got that point? Very good. So obviously you can understand the in-depth analysis capability of the continuous system is much more, because we have both the parameters, space and time, both. Okay, and therefore you can notice that in case of the discrete systems, we were using the normal derivatives, but here we are taking the partial derivatives. Please note, they are partial. Okay, they are not the normal derivatives, they are partial derivatives. Okay, so to put the partial derivatives, and then you can able to solve that. Good. So we get that equation of motion. So now and then we need, and in the previous case, as it is only dependent on the time, we have a single we have, like, suppose whatever the order of the time, that many number of initial conditions we required. Like for example, if we see a single degree freedom system, we need two initial conditions, one in terms of displacement, another in terms of velocity. Once we are having a n degree of freedom system, then 2 into n number of initial conditions we need, n number of displacements and n number of velocities. Okay, but here what happened, we have t and we have x, so we have to check the order of the equation, means order in the domain equation, that what is the order of the x and what is the order of the t. So here in this case, what is the order of x and what is the order of t? Maximum order of x and t both are 2. So if you see that first one is d2u dt2 and second one is d2x d2u dx2. So in both the cases it is the second order derivative. One second order derivative with respect to time, and another case second order derivative with respect to space. So in both the cases we will have two number of initial conditions and two number of boundary conditions that is required. Otherwise we cannot able to solve the equation of motion. Make sense? Suppose if you take the beam equation, then you will see that t term will be similar, it will be second order derivative with respect to t, but it will become a fourth order derivative with respect to space. So in that case, instead of having the two boundary conditions, you will have four boundary conditions to solve it, because space equation is getting increased. And slowly if you go for like a more difficult beams, like suppose thin wall beam, C-section or something like that, it may go to like a 12 order of x, then you will have a 12 boundary conditions, and then that many numbers initial condition. Generally initial condition do not increase, because we generally do not go more than acceleration. So initial condition generally remain up to 2, but boundary condition may increase quite like that, depends on like how much things you are there. I hope you got that idea. Good. So now once we get that, so it also need, so this is my domain equation, this is my domain equation, and then we have another two, that one is boundary condition, and second one is the initial conditions. Make sense? Make sense? Very good. So now if we have this way, then now the next task is to solve the equation of motion. That how can we able to solve it? And our objective is to get what? What are the things known to us? Let's try to count that. Rho is known, that is the density of the beam. A is area of the cross-sectional area, that is also known. E is Young modulus, known. Area already, that is known. What about U? U is not known. And T and X are the variable. So our objective is to find it out U. And additionally, another very important point. Here you can expect the solution of U in terms of X and T both. Because you see, that is a function of X and T. That is not a only function of T. In the previous case, if you try to recall, everything was only the function of time, not the function of X. So life was very simple. Here we have, so now once we are putting some approximate solution, now you have to assume that approximate solution such that it has both the component X and T. And it should be such a manner that it should satisfy all the criteria. Then only you can get a solution. I hope all of you agree with me that where we are standing and what we are looking for. So once we have this type of X as a function of like U as a function of X and T, what is the basic procedure to do that? So any thought, like maybe you have also studied that partial differential equation in your BTech courses, or I should assume, like, as I also forget once I was going to MTech, I also assume your condition that you people also forget that. I think that would be better. Okay, we assume like you forget it, no problem. Let's start. Well, don't worry, I also forget once I went for the MTech. That's true, that happens. Most of the cases, because we did not able to understand in the BTech level what is the necessity of doing the mathematics. That happens, so no problem. So let's think how we can do that. So U of X comma T, we can write it as a function of X and maybe function of T. I will just put it like phi of X into Q of T. So that is known as the variable separation. Okay. If you see that note I have given for the retrospection of mathematics type thing, so there you will found, and I have also mentioned that method, that is a method of variable separation. Okay, because method of variable separation is one of the like a major method what people are used for this type of solving this type of differential equation. Okay, or maybe the partial differential equation rather to see. So now if we write this, that okay, U is phi of X into Q of T. That means what is our aim? We are dividing it into the two parts. We try to look the function as like a how the X is varying and how the T is varying. We are not going into any complicated function where X and T are very implicitly placed. Okay, because there is already so much complexity. Try to remove the complexities or reduce the complexities as much as it can. Okay, so now this method actually has a very big benefit. Why we do that? Because if you see that we need what are the terms there in the equation? One term is del 2u del t2. Now if we assume this way, and now if you take del 2u del t2, then how we should write it? First of all, we are doing the partial. So once we are doing the partial, that means it will only take the t as the variable, but x, all the things will remain constant. So phi x, they are acting like a constant. So differential will act only on the q of t. So what can we write? Phi x into q double dot t. Can I able to write that? All of you agree with me? Agreed? Good. Now, how about this one? Now you tell. This is, yes, phi, not phi double dot, phi double dash. Because dot we are using once we are doing the derivative in terms of time, but dash we are using once we are doing it in terms of x or space. So that will be phi double dash x into qt, because that derivative should be designated differently. They should not be designated with the same symbol. Then there will be confusion. Okay, makes sense? Can you able to write these things? Any doubt up to that? Any doubt? Very good. Now, if we can able to write that, so now if we try to substitute it here, what can we get? Rho a into phi x q double dot t minus ea into phi double dash x into q of t, that will be equal to 0. Yes, agreed? Very good. Now, try to recall again the single degree freedom or multi-degree freedom. Once we are having this type of solution, now here let's see, if we try to think that if we try to see that equation of motion in the time domain, what can we able to understand? Because time domain we have studied so far. So first do with that, then we will think about to go for the spatial domain. Okay. So think how will that be, how will that thing operate? Just like if you think that phi x is like a constant, because that is has no contribution with that t. So that like you can just separate it out. That okay, just assume that is there, but there, okay, I don't care. You just put it phi x and phi double dash x. Just you are trying to dealing with whatever is there with the time. How will you do that? Or how the equation is looking like? Yes, something like that. So it's a second order differential equation with respect to time. Agreed? I think you also want to mean the similar thing. Very good. So how we have solved that? If you think, as he very correctly mentioned, that has a something similarity with this. We generally used to write it like this way. Look, can you able to see the similarity? Just the problem is that yes, now m is not a constant value. M is something a function of x, but that is a function of x, not function of time. So we don't need to be worried, because we are now solving in terms of time, not in terms of space. So for now, we can relax with that point. Okay. And here is also like with a phi double dash of x. Okay. So now how we solve that? In single degree freedom system, please try to recall. What we assume for W? Yes, please. A then lambda t. So in that case, we assume the solution is equal to A into e to the power of lambda t. All of you agree? Or else we can also able to write e to the power of I omega t. That also, because we have seen that that will eventually gives e to the power I omega t. Okay. So in this case, I propose like better we write e to the power I omega t, because we have an idea that it will finally comes and boil down to e to the power I omega t. Okay. So if we just put that u equal to, or maybe like q of t equal to e into e to the power of I omega t, or maybe I just put it like capital Q into e to the power of I omega t. So q double dot will be equal to q into omega square into e to the power of I omega t. Make sense? Okay. So what can I write? Phi a both the q will cancel out. There will be a q also. There will be a q also. Both will be cancelled out because there is 0, so it can cancel out. Okay. If there is no 0, then that q will be staying, and you have to think after that how we can able to solve it. And minus sign we can also able to cancel out. So it will become plus. Make sense? And you can also show what we can say, that omega square rho a plus ea. Sorry, I'm very sorry, very sorry, very sorry. Rho e omega square phi x plus ea double dash phi x e to the power of I omega t, that will be equal to 0. Can I say that? Or even you can say like q into e to the power of omega t, not a problem. If you do not cut q, no issue. Put that. Okay. So that will be equal to 0. Agreed, all of you? Now, if we have this thing which cannot be 0 and which can be 0, what is the scenario? Hmm? Yeah, so that cannot be 0. That cannot be 0. That cannot be 0. Well, if that is 0, then your dynamic portion will automatically become 0. It will as if like it is in state, it is in rest at its initial condition. So that becomes a trivial solution. So we cannot able to have that. So that is cannot be 0. So automatically this leads to one and only solution, that is rho a omega square phi of x plus e a phi double dash x, that is equal to 0. Make sense? Agreed, all of you? Agreed? Good. Now please pay with attention on that. How can I able to solve it? Again, so now first try to see how the equation looks like, what are the scenarios, and what is happening. So if you see very carefully that this is a differential equation in terms of x. With respect to x, we are solving that whole thing. Okay. What is the order of the equation? Second order equation. And we will, so now if we solve that, what can we get? We will get 5x. Okay, very good. So how can we able to assume the solution? And here another very important point is there. In the previous case, if you see, we mentioned that there is a two thing. One is boundary condition and another initial condition. Now initial condition, we will go with this, and we also know how to incorporate the initial conditions. How to incorporate it? We should try to see at t equal to 0 what is the condition, and means all the things. So at t equal to 0 what is the condition? So that coefficients whatever is coming here, we can easily able to address that. There will not be any problem. We can able to incorporate that thing. and there could be two types of different vibrations can happen. One is like you have a free vibration, and another case you maybe have a forced vibration. Now these two will be creating the two different scenarios, because if you see what is this type of solution technique, when we can use this solution technique, is it for free vibration or is it for forced vibration? It is actually for forced vibration, where omega is the forcing. Now don't get confused, for the free vibration case we can do that, but only for single degree freedom. But for multi-degree freedom system, what is omega? You don't know omega, because omega will be 2 or 3 omegas. Whatever the number of degree of freedom, that many omegas will be there. So how can I able to tell that what will be e to the power I omega t? That we cannot able to tell, because that is not a single omega. I think you remember that. We have to do the full model superpositions, and we need to find it out, extract it first, all the natural frequencies, and then we have to do that. So that's the procedure for the free vibration. But here, what we assumed, that's the procedure for harmonic forced vibration, where omega is the excitation frequency. Okay? Agreed, all of you? Any doubt? So here, like, let's say omega bar is the excitation. So that's like, put it omega bar. That will be better, so that we will not get confused. So that will be omega bar. So that is the forcing. So we will do the free also, not a problem. That will have that many number of modes. So yes, we already discussed that it has infinite number of modes. So once we will do the free vibration, that all infinite number of modes will come into picture, and we have to do the summation of all that. Because in case of multi-degree freedom system, we have seen that we have to consider all the modes. So free vibration problem become more difficult in case of the multi-degree freedoms, because all the modes contribution start coming into picture, which you cannot able to neglect. There actually free vibration become easier, because full structure is oscillating in that frequency only, so you don't have any problem. But once you let the structure to vibrate as whatever the way it can, then structure has several problematic things, and they all start vibrating in a more complicated manner. Okay, with like a real life example, you can also think it in that sense. Like suppose people are like a single, they can do it as their own way. Now they're going for marriage and something, so it's become a multi-degree freedom, and maybe then have the children or something. It's becoming like a more complicated multi-degree freedom system. And if there is some forcing, like something happened, then full system will act accordingly. But if you let them free to oscillate, it's a full chaos. It's a full chaos. So it's always we can able to correlate the dynamics in the real life as well. So that way we can able to remember that things also much better manner. Okay, so that's like the scenario, and now it is a continuous. So everything is coupled, and we have infinite number of modes, not one or two modes. Okay, there's a very complicated dynamics altogether. Okay, so we end up here, please. Yes. Force term. Yes, but force you will apply in the boundary. We have not discussed about the boundaries yet. Yeah, force will definitely come, because once we are applying the force will definitely coming into picture, but that will come mostly in the boundary. Because suppose if you have like a system, there could be sometime force can come in the body also, then that is also like we need to then consider it with some other terms will come into picture additional, and then equation of motion will be changed accordingly. Or else if the force is coming, if there was some point in between like a force comes, generally what we do, we divide it into the two continuous system, and then we solve it, because that way our equation of motion is not getting hampered. Because once you are applying the force, if you are taking it in the domain equation, then it has to be like a domain equation. It cannot be like some point it is valid, some point it is not valid. No, that is not possible. Or else, if there is some particular point force acting, you may use the Dirac delta. What is very commonly used for the railway engineering case. Like suppose one load is moving. In that case, once we are solving that type of problem, we wrote the load as like a Dirac of that two term, like x minus vt. Dirac of x minus vt, that actually happens like this way, that once you are changing the time, then its position is changed. And with the Dirac, it is actually telling that it is only applicable at that point where the force is. Other point it will become zero. So you have to be very careful. And now once you use the Dirac function, you will see the life will become complete mess, because that Dirac function you have to only integrate so that you can able to come out from the Dirac function. And now once you integrate over the full domain, equations will become really complicated, because then you are more or less going from the strong form to the weak form. Because in structural dynamics we can do it from both the ways, in strong and weak both. Because here we try to see it in perspective of the differential equation only, so we can solve it in both the ways. But in finite element, it is specifically done from the weak form approach. If you not follow the weak form approach, that is not finite element. There may be something else. Maybe the solution can come properly, but that is not finite element. Finite element is only like once you are expanding it in the weak form, apply the Rayleigh and then do it accordingly, then only it will be the finite element. Otherwise, it's not qualified as a finite element. Okay, makes sense? Very good. So we will also see those cases actually, like once we have a force and all those things, because okay. Yeah, so now this thing is there. Now suppose, let's say we have this bar. Okay, now think that bar could have, so we see that it is a second order differential equation. Okay, second order differential equation in both the side, time and space. So let's try to see what are the initial condition and what are the boundary conditions could be possible. So suppose if you think that you fix that bar in one side and you let one side to them. So what type of boundary condition it should have? So if this is 0, this is L, so you can say that u of 0 comma t, u of 0 comma t, please be careful, 0 comma t, because we are just specifying the boundary condition at the 0 side, which is valid for all the time steps. That is not getting changed. Fixed is remain fixed. That is not getting free after certain time. If that thing happens, then you have to separate that two case. Like suppose you have it and then you're pulling it, and after certain time it got broke and then go out, then you have to model that after breaking as a separate case, not put it into that. Okay, so here like once you are putting it, so let's say that is equal to 0, because you are not having any displacement at that fixed state. Get understood? Good. Then what is this side? How will you write the boundary condition for this side? L comma 0? L comma 0? No, that is the initial. I am saying boundary. First thing boundary. Then we will go to initial. Okay, so boundary. Boundary means always you will have t at that end. Okay, and if you say L comma 0, that is even specific point, not even varying with time, not even varying with space. That is not possible. That's like just a point. You understood that that's a two axis. If you think one is t, one is x. Okay, now once you say 0 comma L, that means you are going into x L and in the t 0, so it's just a point. But here if you say 0 comma t is like a line in that space. You got that point? Now maybe I can draw it. Like you have t, you have x. Okay. Now, once you are put 0 comma t, 0 comma t means you are having a line here. That is 0 comma t. Sorry, wrong. 0 comma t must be here. 0 comma t. Yes. So x is always 0 and you are having something. Okay. At x equal to 0, how it is happening? And that is there is no displacement happening. But if you say 0 comma L, sorry, 0, what you said? L comma 0. L comma 0 means you are just sitting here. That will not serve anything. That is neither, I mean, that is just a point only. So that particular point, that is not qualify as the initial, not qualify as boundary. Okay. So this is one case. Now, what is the another boundary condition? What happening to that side? Yes. Again, L comma 0 is not possible. L comma t, L comma t, L comma 0 means you will be here. U L comma t will be equal to yeah. That if you put some displacement, you are correct that we can put that displacement there. But if you are not putting any displacement, rather if we are applying some forces. Okay, so if displacement, then we can just say whatever the displacements we are applying. So if displacement, that will be also with the function of t, because that should be function of t we have to put. Okay, or else what can we do? If we are having some forces, or maybe we just say that we put some force and then we let it go, or it's just like a free. If it is like a free, how will that be occurring? Means like you just give a displacement and you leave it, you don't bother. So once you give the displacement, maybe that time, for that time it is correct, but other time it, how will you take that? Well, now there is already some displacement, you cannot just directly say also that is 0. So, but there is one thing very essentially is 0, stress. Very good. There is no force, that means there is no stress. Now how can you incorporate the stress here? You are very correct, you are very close to stress. Derivative of u, exactly, because stress means what? So he said that actually, basically he want to mean this. Am I right? That force is 0. Now if you divide the force with area, you will get stress at this equal to 0. Now if you divide it with the Young modulus, you will get your strain is at that point is 0. Now what is strain? Strain is del u over del x of L comma t equal to 0. You got that point? So that becomes your initial boundary condition. Got it? Okay, now the initial conditions. Or initial condition, we can just assume like at initial point some forces were applied and then we leave it, or something like that also we can thought. So that way, like we just say like e to the power I omega t, or maybe we just thinking like okay, particular force we are like keep applying, and that way also we can able to get that. So initial condition we are not considering first, but just first try to see, okay, let's try to see what is happening with this boundary condition and how we can able to resolve this equation with this boundary condition, because these you see there is no contribution of the initial condition now, because time is now gone. So whichever is gone, let it gone. Like what we have now, first try to see that how we can able to incorporate that, and then we will combine both the things and we try to see that okay where we are now. Okay, so we have to satisfy these two things. So first thing is that we have to satisfy, that is u of 0 comma t that is equal to 0 and del u of del x at x equal to L that is equal to 0. And now as there is no t contribution, or maybe I can just say that u of x comma t is equal to nothing but phi of x into e to the power of phi omega bar t. Well, maybe a q is also there. Okay, so now u of 0 comma t will be equal to nothing but q into phi of 0 into e to the power of phi of omega bar t. Okay, and that is equal to 0. That's my first equation. Okay, so what is 0 here? Q cannot be 0 because q is the amplitude of that e to the power I omega bar t. That also cannot be 0. So what can be 0? That is only phi of 0 is equal to 0. Okay, that's the only possibility. No other possibility can be possible. Okay, agreed? Good. What's next? So again u of xt was q into phi x into e to the power of phi omega bar t. So what will be del u del x? Q into phi dash x e to the power of phi omega bar t, that will be again equal to 0. Okay, that is at x equal to L, that is 0. So that is x equal to L. So now if you see, that is q into phi dash L e to the power of phi omega bar t, that will be equal to 0. So now you can say phi dash L equal to 0. Can we say that? Can we say that? Is that okay? Perfect. If it is okay, now so if I think, that is my equation 1, this is my equation 2, this is my equation 3. So what was our target? We should not forget that, like what we actually want to do. So what is phi x? So we need to find out what is the expression for the phi x that we are trying to solve here. Okay, good. So we need the solution of phi x which should satisfy the domain equation given in equation 1 and with the two boundary conditions given in 2 and 3. Agreed? All of you? Agreed? Very good. Now, so to do that, how should we proceed? That is again a differential equation. So phi x, we have to find it out. What is the order of the differential equation? The first question is that come, what is the order of the differential equation? Then again I will try to get the solution. So this is the order of second order. So can I say that solution of phi x is something like that, summation of j equal to 1 to 2 aj into e to the power of lambda jx, or if I just simply write a1 e to the power of lambda 1x plus a2 e to the power of lambda 2x. Can I say that? Or else we just write, assume like a into e to the power of lambda x, put it, solve the value of lambda. We will definitely found the two roots of lambda. One will be lambda 1, another will be lambda 2. That's the way we did in that all the cases. So maybe we can just assume that this is like phi of x equal to a into e to the power of lambda x. So now substitute it. So if I substitute it, not a, or maybe a can be cancelled out also here. So maybe just wait a minute. So if I rewrite the equation of motion, then it will be phi of x plus e into phi double dash x, that is equal to 0. So now if I just substituting, so that is my equation 1. If I now substituting this one in equation 1, then what I can get? Rho omega square into A into e to the power lambda x plus E. What will be phi double dash x? Phi double dash x will be lambda square E to the power of lambda x. So E lambda square E to the power of lambda x, that is equal to 0. Agreed? All of you? Good. So rho omega square plus E lambda square equal to 0, because A and e to the power lambda x cannot be 0. Okay. So what will be the root? Lambda square equal to minus rho by E into omega square. Make sense? So that will be equal to I into plus minus I into this. Okay. So what can be my solution? Phi of x solution is a1 into e to the power of I root over of rho by E omega x plus by omega bar x, usually omega bar, because this is the forcing, so omega bar x plus a1 then a2 e to the power of minus I rho E omega bar x. So that can be also written as phi x equal to maybe c1 into cos root over of rho E omega bar x plus c2 sine root over of rho E omega bar x. Okay, that we can write. Okay, all of you okay with that? Okay, what is unknown here? What is unknown here? Yes, no, omega bar is known term. So let's see. Rho is known, E is known, omega bar is known, x is a variable. Here also same thing. X is variable. C1 and C2 is unknown. So how to calculate C1 and C2? Boundary condition. Initial condition we have not discussed. Because still we are with the x. We did not came out from x. So first let's finalize the x and then we will come out to t and then we will discuss that. So C1 and C2 we have to find out from the these two equation 2 and equation 3. Yes, please.
So we are forced to use zero.
Sorry?
If we are forced to zero, then how we are getting omega bar?
Force we are not assuming exactly 0. Means we are just thinking that maybe your structure is oscillating with some sort of particular frequencies and that is like already driven. Okay, so we can also put the force. You will see if we put the force, what will happen, you know, that will add another forcing term there. Nothing else will happen additionally. Okay, but I did not first try to put it as like a free vibration problem. Then you can understood that we have to expand it full thing and the conception will not be able to clear. Okay, so for the beginning point, first assume there is some forcing term, but obviously I understood that where is the problem happening, that you are thinking okay there is a force, that's why the forcing terms frequency is coming, but what is the amplitude, why it is not considered in the equation? That I agree with your point, but just like for time being assume that that is there something, we will consider that throughout that thing. Okay, or in the maximum scenario what you can think is like that is not getting 0, it has some value. Then again you can solve that full thing and you will get that one. Okay. Okay, so we got up to that stage. So now if we substitute that one back there, we can able to solve what is the value of C1 and C2. Make sense? Because we can do the derivative with respect to x here, and then C1 C2 is coming there, and we can able to solve how it is coming. Perfect. Good. So once the C1 C2 is come out from here, now what we can say, that our Q is ready. Sorry, our phi is ready. Our phi x, we will get a complete expression which is satisfying the boundary conditions. Okay, so once this is done, we will satisfying the boundary conditions. That is satisfied, and we are having a expression for the phi. That this is my phi. Within this domain, this will vary like this way. Okay, but still one thing is left, that is we have not talked about the initial conditions, that how initial conditions are acting. Now think that this is like a shape, or you are saying that okay, my variation is like that, and that variation you are just scaling up and down as like a mode shapes. What do you do in case of the mode shape? Mode shape is there, and once we are doing the vibrations, then we say that okay, these mode shapes is actually scaling up and down with respect to the Q. There also we like have that Q we multiplied with that mode shape, so you are doing it. So that mode shape is scaled, sometime more, sometime less, sometime negative, positive. That way this thing is happening. So that's the way how we should try to figure out the full thing. Okay. Now maybe if I come back to your question, that if we do not have the force, where will be the problem? Now you see, if you try to solve it, you actually cannot able to solve it. Why? Exactly, that both the things are zero. So once you will put, you will basically have some matrix with C1 C2, that is 0 0. Okay, so now once this is coming like this way, that these C1 C2 and 0 0, you cannot able to solve it, because C1 C2 will automatically become 0 and 0. So you see, you need that forcing term. I got that point. So in some point, like suppose if you are applying a force here, let's say, so like you are just applying it to the power of I omega bar t. So then what will happen? This place your force term should be there. Okay, so then that will not be 0. That will have some value, and you can able to calculate. Okay, this is my system. That C1 C2 will be properly calculated. Got that point? So that's why that force in a particular point can be considered. Okay. And once we are applying the force, and at that case initially, and initial condition, suppose if we are now thinking, so suppose let's say we have given the force here, so assume this is something force divided by area divided by Young modulus times e to the power of I omega bar t, some force. So that will become F divided by A into E. This is that will it will come. Okay. So now if I just put, so that may be cos of lambda x then sine of lambda x. So that will be, so if I do the derivative, so that will become how much? Minus lambda c1 sine lambda x plus lambda c2 cos lambda x. Okay, so if I just try to put that in the matrix form, then we will have C lambda, S lambda, and here we will have minus lambda S lambda, and that is lambda C lambda. So just let me write it here. We will have like a cos lambda x, sin lambda x. Here we will have minus lambda sin lambda x, and here you will have lambda cos lambda x. And in the first case, that is 0, x you are putting 0, and here you are putting L instead of x. Okay, so first term will become 1, and that is become 0. That is with C1 C2, that will be equal to 0, and that is F divided by E. Okay, okay, so if you can able to solve it, because you can just take the inverse of that and you can put it here, and you can able to get some value of C1 C2. So once you get the some value of C1 C2, then you will can able to express C1 into e to the power of cos lambda x plus C2 into sin lambda x. Done. That way you can able to write that. Now comes to the initial condition. So now initial condition, so initial condition, if we say that, so if I just go back to here, so you see that boundary condition means something we are specifying here, and another case we are specifying something here. Okay, at x equal to 0 and x equal to L. Okay, that's the boundary conditions. So these are the boundary conditions. Okay, which are throughout the time. But in case of the initial condition, what do we have to do? We have to specify it here. What is happening here? Make sense? That thing we have to specify. So what type of initial condition can be possible here? Additionally, I would like to point one point. If you try to recall that what happened in case of the single degree freedom system, force vibration, because this already we understood this is a force vibration problem. We have also incorporated the force, but we had a mind that okay, where is the force? Now we have also seen that where is the force. Okay, so there is now no confusion, and we considered the force as a boundary condition here. Now try to recall the case of the single degree freedom or multi degree freedom system force vibration. In case of the force vibration, do we need the initial condition? No, yes, what? Some people seems like thinking no, some people seems like thinking yes. So what is the correct answer? Actually, if you recall properly, that if we have initial condition, then what happened? Then we have a transient phase. And then we go to the steady state. In the steady state, initial condition is not required. That's the correct statement. That in steady state, initial condition effect is not required. But in transient state, it is required. But here, what we have solved? Here we doing the force vibration. So if we are interested to know the transient part of the vibration, then initial condition is required. But if we do not bother with the transient state of vibration, we are just happy with the forced, like a steady state vibrations, we don't need the initial condition. Agreed? Which is matching with the previously what we have studied also. So if we are first be happy with the steady state only, then we will think okay, how we can include the transient as well, because for including the transient we have to first solve the free vibration. Without solving the free vibration we cannot include the transient, because transient is like a transition from its own property to the forcing properties. Okay, so that thing is the transient. Okay, so that thing we need to keep for the next class, that okay, how we will do the FRIO, and then we can able to get there. But so the forced one, so the steady, if you see what is exactly happening here, so we get the how the system is actually looking like. So maybe you found that okay, this person is fixed, so your displacement is increasing like that. Obviously not in the perpendicular direction, in the horizontal direction, but I cannot plot in the horizontal direction. So I just assume it like plotting happening the horizontal, I mean along the axial direction, but I plotted in the vertically up. Okay, makes sense. So now this full thing is like your phi of x. So that phi of x is changing with the time. So that is like at some point that is here, at some point this is here, at some point this is here, like this way this phi x is changing. And you are looking at the solutions of that. Any confusion? And this shape is not a straight line. Now think, if you do it as a single degree freedom system, you would get a straight line. Means that approximation, if you do it like this, then what will happen? This point you have a value, and you have a value at this point. So you can just only draw a straight line. So you are thinking that a straight line is moving like this. But here you are having a very rich function which is made of sine and cosine. So it's like a very higher order polynomial, not even a smaller order. Because sine cosine is like almost like infinite terms are there in the polynomial series. So that higher order polynomial you are considering, and you are looking at how the shape is actually evolving and how the displacement field is changing. You got that idea? And yeah, I'm coming. And if you think in the multi-degree freedom system, what is happening? Instead of having like a 1 point, you are maybe like discretizing into 4. So you will have like a 1, 2, 3, 4, and they are all possible modes. Like once it is a 4, so that has these 4 modes. So that 4 modes combination is giving you something, and from there you are doing it. So that's a scenario, whole thing. So one case you are actually solving with some linearly approximated systems, and another case you are just taking a continuous function. So obviously, no question, this is the most accurate, or this is almost like exact. As per, means if your mathematical model equation of motion is correct, then this is exact solution. But these all are the approximate solutions. And now obviously it depends on how much approximation you need. Suppose if you want to send some satellite to moon, definitely you need a very much accuracy. Or if you are making a building, maybe not that much of accuracy is required. That thing can be considered in the factor of safety and all those things. So definitely that accuracy level you have to satisfy, and you have to judge, and based on that you have to make your model. I think you got that point. So in next class we will try to see how we will do the free vibration, so that we can able to get that full story. Thank you very much.